Welcome to Maths with EJD. In this video, I'll be talking about sequences of real numbers. Sequences of real numbers. Of course, still talking about real analysis in general. So let's look at some core definitions when we talk about sequences of real numbers. By the way, a sequence, of course, since we're talking about sequences, the first thing we like to talk about is a sequence. I mean, in the regular term, right? Because I remember I have a playlist on sequences and series. A sequence is simply a pattern of numbers, basically. Maybe you have repeated addition, repeated subtraction, or some other rules being obeyed, or I mean, subs or consecutive squares, consecutive cubes. It can come in whatever form, and some are even bound by some kind of formulas, right? So, first of all, in the context of real analysis, let's talk about what a sequence looks like. A sequence in real numbers is a function A such that natural numbers are mapped to real numbers. And that is written as an, given that n is greater than or equal to 1. So in essence, we are saying that there's an A1, there's an A2, there's an A3, there's an A4, and all these numbers are actually real numbers, right? So then we talk about convergence. We already saw the idea of convergence like in the previous video and the interconnection between convergence and boundedness, right? So here we talk about convergence. So we have the sequence an approaching a limit L, which is a real number, right? If so, convergence this is the definition of convergence. That's what basically you're saying here, that a sequence an, you know, approaches L or converges to L, which is a real number. L is an element of real numbers. If for all epsilon greater than 0, for all small positive values of epsilon, that is, there exists a particular big N for all n greater than or equal to big N, such that the absolute value of the difference between an and L is less than that epsilon. So it's telling us that, as you take subsequent values of an, maybe as you take a1, a2, a3, as you continue to find the difference between each value of an and the limit to which it tends, so the absolute value is always less than that small value epsilon. Basically, that's the whole idea. So of convergence in this case. And then we go ahead to talk about a Cauchy sequence. Okay, we saw something about Cauchy in the previous video. The sequence an is Cauchy if for all epsilon greater than 0, there exists a big N for all m and n greater than or equal to that big N, such that the absolute value of an minus am is less than epsilon. We had something like this in the previous video when we talked about Cauchy completeness. Then we have a bounded sequence. So for a bounded sequence, right, there exists a particular big M greater than 0, such that the absolute value of the sequence is always less than or equal to M. So this is a functional definition of boundedness. But then, of course, like we saw in the previous video, we can connect boundedness and convergence, and this happens for all values of n. So it means if you have a sequence of numbers a1, a2, a3, a4, so any of the ANs you take, and you take its absolute value, whatever it is, it will always be less than or equal to that big M, for any value of n. Then we talk about subsequential limits. So that's talking about the fact that you have a sequence and you have a subsequence of that sequence, and that also has a limit. So, we use capital L normally for the limit of the sequence itself. For a subsequential limit, let's look at small l. So if we have a small l, which is a real number, is subsequential. So that l, which is a real number, is a subsequential limit if there exists a subsequence ank with ank approaching L. Just like A N here was approaching L. So that subsequence is approaching that small L. That's when you say that small L is a subsequential limit. So let's move on to completeness and convergence. Of course, in the previous video, we had talked about completeness, you know, uh, of real numbers, but here we are also talking about something in that line. And then this first theorem, I think we're able to prove it that convergence implies Cauchy and Cauchy implies convergence, right? So we have a theorem about completeness and convergence. So theorem that in the real number system, a sequence converges if and only if it is Cauchy. And if and only if simply means that if a sequence converges, then it means it's a Cauchy sequence. And if it's a Cauchy sequence, it means it is a convergent sequence. And we have a proof sketch for that. I mean, we did something like this in the previous video. So if an approaches L, so if it converges to L, that is, then the absolute value of an minus am less than or equal to absolute value of an minus L plus an minus L, like that. And that means that happens for small which is small for large M and N, right? As M and N are increasing, you have this happening more and more. So what is basically happening here is that we have okay, I think at some point I may need to just do some writing to maybe just a little bit of writing that is so just to demonstrate some of these things. Let me open like a new note here. Yeah. How did I used to do it? Let me see. It's been a long time since I ever wrote here. No, this doesn't work. Um, should I say more? How did I used to do it? It's been a long, long time. Okay, let me just add page here so I don't bother myself too much. Okay, so if you look at what is happening here now, so if you look at this now, we have, okay, can I copy this? I don't know. Oh, okay. I guess I can snip it new. Okay, because I'm still coming back here later. I don't want to keep going back and forth. So let me just do a rectangle. So I just have this. Nah. Oh, okay. Yeah, this is wasting my time. Okay, let me just close this. Okay, we just have the an minus a. If converges to L, right? And we have an minus am, and then it's broken down this way. I just want to show why we have that expression. So we have that you have an going to L, implying that the absolute value of an minus am, okay, is now is that less than now? Okay, is that less than? Let me see. Yeah, less than or equal to all that. So we have less than or equal to. So we say this is less than or equal to. So you can imagine it like an minus L, all right? Um, of course, plus L minus am. So of course, technically you can cancel these two out because it's basically zero. So those are some tricks when we do this kind of thing here. Okay. So here now, so you now want to standardize the idea that this is now less than or equal to um absolute value of an minus L plus absolute value of L minus AM. And since we're talking about the idea of absolute value, this is still the same thing as AN minus L plus, if you reverse it, it's the same. AM minus L. And that's what we have there. So, I mean, the idea of the reversal is this. Absolute value of 2 minus 3 is the same thing as absolute value of 3 minus 2. So it doesn't matter if you have AN minus L or AN minus or L minus AM. Okay? So that's what is basically happening in that place. So back here now, so you see that an as if an approaches L, then absolute value of an minus am is less than or equal to absolute value of an minus L plus absolute value of an minus L. So this is small for large M and N. Okay. I mean, we are saying that this whole expression is small. I mean, the idea of smallness is that where we bring in the whole thing about this now being less than epsilon, which is greater than zero. Okay, so that's the idea of it being small right there. So it is small for large values of M and N. That's the implication. So if sequence AN is Cauchy, it means it is bounded, right? But Bolzano-Weierstrass, by Bolzano-Weierstrass rather, it has a convergent subsequence ANK, which approaches L again, or some small l. So Cauchiness forces all terms to converge to L. Yeah, that's another one right there. So Cauchiness is now even telling us that any subsequence you pick from a Cauchy sequence, it will always converge to the same limit L. So then we have the Bolzano-Weierstrass. So which says that every bounded sequence in R has a convergent subsequence. And then this tells us now that that point of convergence will be that L for the sequence and for the subsequence, like that. Okay, now let's talk about uniqueness and algebra of limits. Uniqueness and algebra of limits. So talking about uniqueness, if AN approaches L, if AN converges to L and AN converges to M at the same time, then we can simply say L and M are the same, right? So if one sequence converges to two different limits, then we can say that those two different limits are actually not different limits, they're actually the same thing. All right. So then we go for proof. So for epsilon greater than 0, of course, that is small epsilon, like 0.00001 or anything like that. Eventually, the absolute value of an minus L is less than epsilon divided by 2, and the absolute value of an minus m is less than epsilon all over 2. Then in that case, we can say the absolute value of L minus M is less than epsilon, because of course, if you add the two together, you have epsilon over 2 plus epsilon over 2, that's epsilon. So letting epsilon go towards 0 gives L equals M. So it means that if we say that absolute value of L minus M is equal to 0, because epsilon is very tiny and it approaches 0. So if we say Lm is 0, then we are simply saying that that L is equal to M, basically, and that is the proof for this expression up here. Okay, so we see the algebra that AN plus or minus BN approaches A plus B. So these are some like laws of limits now. So if you have sequences AN plus or minus BN, so the limits, right, of sequence AN plus BN will be A plus B, and for AN minus BN it will be A minus B. Then the limit for sequence CAN will simply be equal to CA for C, which is also real, right? Then the limit of sequence A and Bn multiplied by Bn will simply be A multiplied by B. So it's more like the limit of a product is the product of their limits, of the limits of the parts we are multiplying. Then if you say B, if you take B to be 0 and Bn is also 0, eventually then the limit of the sequence AN over Bn will simply be equal to A, will be, I mean, the AN over Bn will simply approach big A over big B, like that. Then let's talk about the idea of limit supremum and limit infimum. So define that Sn is the supremum for k greater than or equal to n. So the supremum of ak, Sn is the supremum of the sequence ak for k greater than or equal to n, and In is the infimum of sequence ak for k greater than or equal to n. All right. Then we can say that the sequence Sn is decreasing and In is increasing, both converge in R bar, that's the set of real numbers, the bar of that, the complement of that, I want to think. So then you have the definition that the limit of the supremum of AN as n tends to infinity is the limit of is the limit of this Sn now, as n tends to infinity. And then the limit of the infimum of AN, all right, we already have of a particular AN as n tends to infinity is simply the same thing as the limit of the infimum In as n approaches infinity. So we have the limit of supremum and the limit of infimum. Okay, so and we have some properties like that. So the limit of infimum AN is less than or equal to the limit of supremum AN. And then we also have the fact that if if AN converges to L, then it implies that the limit of the infimum AN is equal to the limit of the supremum AN, which is equal to L. All right. So, and of course, you can also take that back, that the limit of infimum AN is equal to the limit of supremum AN equals L implies that AN approaches L. AN has the limit L or converges towards L, like that. So, by the way, limit of Limsup is the largest subsequential limit, while Liminf is the smallest subsequential limit, like that. So, and then we have the idea of identities for Limsup and Liminf. So, the limit of the supremum of sequence minus AN will be minus limit of the infimum of an. So that behaves like some kind of what we call in calculus, that's more like some like odd function, something like that. Not quite, but that's an idea to just talk about it. And the limit of infimum minus an is the same thing as minus limit of supremum an, like that. So the limit of supremum an plus bn is less than or equal to limit of supremum an plus limit of supremum bn. So that's more like the limit of the sup of a sum of sequences is less than or equal to the limit of the limits of each of the supremums of the two different sequences. So if C is greater than or equal to 0, limit of the sup CAN is equal to C now, the limit of sup AN. If C is less than or equal to 0, the limit of sup CAN will be C limit of infimum AN, like that. So that those are some very nice identities to think about. If an approaches A, then the limit of the supremum an plus bn is A plus the limit of supremum bn, like that. That's if an approaches A, and we don't know what bn is approaching. So then we have the Stolz-Cesaro theorem. The Stolz-Cesaro theorem. Now, most of the times when you hear these big names, they are not really that big. But I mean, the name just makes it look like it's one big term. So let's look at what the Stolz-Cesaro theorem talks about. Suppose xn is strictly increasing with xn approaching infinity, right? Okay, so it means we now say if the limit as n approaches infinity of yn plus 1 over yn, I mean yn plus 1 minus yn over xn plus 1 minus xn approaches the limit, right? So we are simply talking about some differentiation kind of thing here, right? Then we can say that the limit as n approaches infinity of yn over xn is equal to L in this case. And then we can have a special case that if xn is equal to n, actually, so like xn is equal to n, then we can say that the limit as n approaches infinity of yn plus 1 minus yn is equal to limit, which implies that the limit as n approaches infinity of yn over n is equal to L. So that's the special case of the Stolz-Cesaro theorem. And you can see it's already looking like a slope, because this is yn plus 1 minus yn over xn plus 1 minus xn. And that's the whole idea of limits. Okay, without limits, we can it's difficult to talk about differentiation, for instance. So let's see a classic example of the Stolz-Cesaro theorem. Now look at this. We have a bound like log 1 plus x is always less than or equal to x, right? So so for instance, if you take log 2, it's always 0 point something. Log 10 is 1. I mean, log 10 base 10 is 1, for instance, like that. So log 1 plus x is always less than or equal to x. That means that, and that implies that log to base an is equal to n log 1 plus 1 over n, right? So if that is the case, now basically what's happening here, okay, this is log to base an, right? So, and then you have n log 1 plus 1 over n, like that. Okay, because if you want to take away this x from here now, oh no, this is x, right? And then it's more like divide both sides by x. No, okay, so log to base log a to a sub n is now n log 1 plus 1 over 1 less than or equal to 1. And that implies that an is less than or equal to that's e. E is 2.718, like that. Then we have monotonicity. So for monotonicity, we define f of x to be equal to x log 1 plus 1 over x. Then in that case, f prime of x would be, of course, if you want to deal with this, right? If you keep this constant, you differentiate x, you get log 1 plus 1 over x. And then if you keep x constant and you differentiate 1 plus 1 over x, then you end up getting 1 over 1, or 1 over 1 plus x greater than or equal to 0. So in that case, now we say that, in this case, you see that f prime of x is log 1 plus 1 over x minus 1 over 1 plus x, which is greater than or equal to 0. So in that case, we say that an is increasing in that sense. So in conclusion, now we see the sequence an is monotone increasing. It is bounded above by by E, and hence an approaches E. And that's how the idea of the exponential term, is it the exponential exponent, right? E raised power x. That's how e raised power x came about. So from the idea that 1 plus 1 over n. So as this is increasing, it is moving fast towards the value E, like that. And then we have we have to talk about constructing sequences with given limsup and liminf. Very simply, given that L is less than U, that is a particular limit L is less than U, and we define that A sub 2k, like a subsequence, is equal to U minus 2 raised by minus k, and A sub 2k plus 1 is equal to L plus 2 raised by minus k. Then the limit of the sup of the supremum an is U, while the limit of the infimum an is L, like that. That's just how to construct sequences given limsup and liminf like that. Okay, so let's talk about some more classic limits. For instance, if you have if the absolute value of R is equal to 1. I mean, another way to express this is to say that okay, I think I should write here. So absolute value of R is less than 1 simply means that, so the absolute value of R less than 1. Another way to say that is that minus 1 is less than R and R is less than 1. That means that R simply lies between minus 1 and 1. That's the implication of such an expression, right? So if R lies between minus 1 and 1, basically we are saying that then R raised power n always approaches 0. Okay? So because if R lies between minus 1 and 1, it means that in fact I think it makes a lot of sense because absolute value of R is less than 1 implies that minus 1 is less than R less than 1. So that means that it never gets to minus 1, it never gets to 1. So it means, yeah, okay, if you want to take it to one decimal place, it means you have like a closed interval of like 0.9, I mean, minus 0.9 and 0.9, okay? And if you square any of this, because it's one decimal place, right? If you square 0.9 or minus 0.9 and 0.9, you're going to get like 0.81. So, and that's even smaller than 0.1. And, that's why the square of that will be approaching 0, like that. Then we have another one that the log of n over n raised power alpha approaches 0 for any alpha greater than 0. So for any alpha greater than 0, the log of n over n raised power alpha approaches 0. Then if the limit of the supremum of an raised by 1 over n is less than 1, then an itself is approaching 0. Then if the limit of the supremum of an plus 1 over an, the absolute value is less than 1, then an approaches 0 also. So these are some classical limits to think about. Okay, so yeah, we have some problems we want to try out based on the things we have considered so far. So prove that 1 plus 1 over n raised by n is increasing and bounded above by e. So we saw something close to that already. Then show that an over bn approaches a over b if an approaches a and bn approaches b, where b is not equal to 0, because if b is not equal to 0, this will be undefined. So we've seen something like that before. It's just that to show that, okay, because the top is approaching A, the bottom is approaching B. So it's just basic logic like that. Then you want to verify that the limit of the supremum minus an is equal to minus limit of the infimum an. Then you want to build this sequence an with lim sub an equals 1 and lim sub an equals 0. I think we saw something like this before where we talked about construction like that, something like this. We can build that. Then we want to apply the Stolz Cesaro to compute lim as n approaches infinity of summation from k equals 1 to n of log 1 plus 1 over k over log n. So the hint here, the numerator simplifies to log n plus 1. So this numerator up here simplifies to log n plus 1, and then you can take it up from there. So you want to try your hands on that and let me know your results in the comment section either on Facebook or on YouTube. So with this, I come to the end of this interesting video. Let me know how helpful this is for you. And of course, if you have not subscribed already, you want to go ahead and subscribe right away because you don't want to miss anything again on this channel. So after subscribing, don't forget to hit the notification bell so you can always get alerted each time a new video is released, right? Having subscribed, you want to take it a step further. You want to become a member of this channel by clicking on join, and you can see 3 different levels of membership with some special privileges that you really like to enjoy, right? Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.